Hello. Hello, everyone. Hello, everyone. Can you hear me?
I can hear you, Jabulani.
Okay.
I see we've got 71.
I'm wondering what's happening with my screen. You just get my slide to be on view. Okay, yeah, so we just to get things started, we will try and get our house rules in order. But nevertheless, let me just make sure that we all can see the screen. Can you guys see my screen?
Yeah, it says GoToWebinar. It hasn't got the presentation on.
Okay.
There you go.
I think you can just work off you can just work off my screen, Jabulani. Go ahead.
Okay, you can put up your screen. That's fine. Yes. Thanks, Leslie. Okay, thank you. Okay, so I'll just go through it and then you will just change slide up according to Wesley. Okay, so good afternoon, everybody. We thank you for joining us. Thank you for taking your time once again to be with us today for this for today's webinar. And as you all know, the topic of today's discussion is introducing rotating machines section. So we're looking forward to you and your friends and whoever is interested in machines joining us. Just to look at the house rules, housekeeping rules, we've been asked that you switch off your webcam so that we don't overburden the system. And also, in terms of the questions, you would obviously, like you to ask questions at the end of the presentation of each speaker. You feel free to ask questions. Those you can do that by looking at the side of the screen. There's a question feature on the side. Please use that to ask questions. And also, what we would appreciate is that we would make the material available to those who are interested. But most importantly, if you really want to find more, not only this material, but more about rotating machinery or machines section, please look on our website. There will be more information as well, including this one. So I just want to find out the reason why you're here today and why you should stay with us. Leslie, can you just move on to the agenda, please? Hello, Wesley. Can you move to the next slide? Okay. My name is Jabulani, as I've indicated. I'm a current chair of the rotating machinery section, and I'll be helping out with the presentation. And my co-host is Dr. Wesley Doorsamy, and as you see his resume and my resume on the screen. Feel free to have a look at it. We don't want to bore you with all this, but you've shown your spare time, you've had a look. The real people that we're looking forward to are the presenters. And let's just go over the agenda as to what is on the plate today. Well, we're looking forward to the presentation by Dillan Ockhuis, whose project was the best at SAUPEC 2020. And the title of the project was Impedance Matching of Direct Grid Connected Renewables Energy Synchronous Generators. I'm sure you two are looking forward to that. We've mentioned a brief of this in our previous forum meeting, where we wanted to find out what is happening in the renewable space. And Dillan will help us find out some of the gist within that industry. Well, then after that, we're looking forward to Henry as well. He'll be looking at the preview of RMS courses, that is the rotating machinery section courses. And Henry's topic is overview on the motor theory and management. And I'm sure all of us are very interested in finding out how to manage our motors, especially now that some of these motors are running by themselves out there. We're not there because of the situation that we're currently facing. And after that, we'll have Dr. Lissetti, and he will look at the overview of electric drives and their applications. And that is it's a very pertinent topic, and we're all looking forward to that discussion to find out what is happening in technology with regard to the electric drives and the application. And thereafter, we'll have Rob Malaya. He will look at overview on industrial rotating machinery or rotating machines. So please feel free to relax, and I'm sure you're going to be entertained, and you'll get more information from these people. Like I mentioned in the introduction, that among these people, you're looking at more than 80 years of experience. So I'm sure you'll enjoy. For the rest of the program, I'll give over to my co-host, my colleague, Dr. Wesley Doorsamy, to take you through. Thanks, Dr. Doorsamy.
Okay, thank you, Chair Jabulani. So I'm just going to introduce our first speaker, Mr. Aukes. He received the Best Performing Student Award at SAUPEC 2020, and he was given this award by the Rotating Machines Section. Mr. Aukes received the degree in 2016 and the MH degree in 2018, both in electrical engineering at the University of Stellenbosch. He's currently working towards the PhD degree at the Department of Electrical and Electronic Engineering at Stellenbosch. His current research interests include the connection of renewable energy systems to the grid, with a specific focus on wind turbine systems. So there will be time for questions after Dillan gives us his presentation. Please use the questions panel on your right-hand side to post your questions, and we have some time afterwards where we'd like to engage with Dillan on his research and his presentation. So Dillan, over to you.
Thank you very much for that introduction. Good afternoon, everybody. As was mentioned, I'm Dillan Ockhuis, and I'm from Stellenbosch University, and my SAUPEC paper is about the impedance matching of direct grid connected renewable energy synchronous generators. My presentation is outlined as follows. I'll provide a brief background surrounding the problem before getting into what the purpose and the aims of the paper is, followed by the analysis and some results, and concluding with the conclusions. As the ratio of inverter interface renewable energy sources increases, future power systems may experience a reduced short circuit strength due to the lack of rotational inertia present in the system. When a power system short circuit strength is insufficient, it becomes more susceptible to voltage instability caused by load changes or faults. This issue is especially relevant to microgrids, which are typically located in weak areas of the grid and predominantly comprise of inverter interface, solar PV, and wind turbine systems. This problem is further exacerbated when the microgrid operates in islanding mode, where the main grid is no longer available to supply a fixed reference voltage for the inverters or to supply the short circuit current required to trip the circuit breakers within the microgrid. Synchronous generators are strong voltage sources capable of supplying large amounts of short circuit current in the event of a grid fault. Consequently, connecting synchronous generators directly to microgrids has the advantage of increasing the system's inertia, while increasing the system's dynamic stability, while making the system less susceptible to voltage fluctuations. If the synchronous generator can form part of a renewable energy source, it is further advantageous. Two applications of direct grid connected synchronous generators include small hydropower systems and the slip synchronous wind turbine system, which is the focus of this paper. The slip synchronous wind turbine system consists of fixed speed turbine blades, which is connected to a slip permanent magnetic coupling, or SPMC, which itself is connected to a conventional permanent magnet synchronous generator, or PMSG. The slip synchronous wind turbine system is directly connected to the grid by means of a grid connection controller, It should be noted that once grid connected, power flows directly from the generator to the grid without first flowing through the grid connection controller, or GCC. However, the fixed flux nature of the permanent magnet synchronous generator means that its performance is highly susceptible to grid voltage variations, and its efficiency is particularly low at low wind speeds. This issue can be mitigated to some extent by increasing the impedance between the generator and the point of common coupling, or PCC, as is shown in this slide. However, ideally, this external impedance would be built into the design of the generator rather than being an externally added component. The purpose and aim of this paper is to evaluate how an added impedance influences the generator's performance in terms of efficiency, reactive power, and grid current. The effect of the magnitude of the generator's back EMF voltage on the overall performance is also investigated. In the modeling is done on a per unit basis using the equivalent circuit and phasor diagram as shown. From the circuit diagram and phasor diagram, expressions for the output power, reactive power, grid current, and efficiency can be derived. In the analysis, the stator resistance and core losses are kept constant at 0.05 per unit and 0.02 per unit, respectively. The synchronous generator's synchronous reactance and back EMF voltage are also varied in the ranges of 0.1 to 1 per unit for the synchronous reactance and 0.95 to 1.05 per unit for the back EMF voltage. The grid supply power and grid voltage are also varied between 0.2 and 1 per unit for the supply power and 0.9 and 1.1 per unit for the grid voltage. This slide shows the analytical results of efficiency versus grid voltage and supply power for 3 selected values of synchronous reactances, namely a synchronous reactance of 0.2 per unit as indicated by the red, 0.5 per unit as indicated by the dashed blue, and 0.8 per unit as indicated by the black curves. 2 scenarios were identified where the back EMF voltage was 1 per unit and 1.05 per unit respectively. For these 2 figures, it should be noted that the top portion of the curves indicate where the supply power was kept constant at 1 per unit, and the bottom portion of the curves indicate where the supply power was kept constant at 0.2 per unit. As can be seen, the efficiency is particularly low for small values of synchronous reactance. However, good overall results are obtained for a synchronous reactance of 0.5 per unit for both considered values of back EMF voltage. The slide shows the analytical results for the reactive power versus grid voltage and supply power for the same 3 considered synchronous reactance values in the same 2 scenarios of back EMF voltage. However, for these curves, the top portion of the curves indicate where the supply power was kept constant at 0.2 per unit, and the bottom portion of the curves indicate where the supply power was kept constant at 1 per unit. As can be seen, the best results are obtained for a back EMF voltage of 1.05 per unit and a synchronous reactance of either 0.2 per unit or 0.5 per unit. Finally, the slide shows the analytical results for grid current versus grid voltage and supply power for the same 3 synchronous reactance values and the same 2 scenarios for back EMF voltage. Once again, it can be seen that the best results are obtained for a back EMF voltage of 1.05 per unit and a synchronous reactance of 0.5 per unit. Typically, what we're looking for here is low variation in grid current as the grid voltage varies. In order to verify the analytical results, a slipped synchronous permanent magnet generator was placed on a mechanical test bench. The generator was driven by an induction motor and variable speed drive, or VSD. The variable speed drive and the induction motor is responsible for maintaining the synchronous generator speed at synchronous speed prior to grid connection. A set of synchronization lights and an oscilloscope are used to connect the synchronous generator to the grid once the relevant grid connection criteria have been adhered to. Once grid connected, the voltage at the terminals of the generator can be varied by means of a variac, and the supply power to the generator can be varied by changing the speed reference voltage, given to the induction motor. However, before any grid connection tests can be conducted, an indication of what this particular generator's synchronous reactance and back EMF voltage values are needs to be determined. In order to do that, an open circuit and short circuit test was conducted. The open circuit and short circuit test revealed that for this particular generator, it has a synchronous reactance value of around 0.17 per unit and a back EMF voltage of around 1.03 per unit. This table also shows some of the relevant parameters of the considered generator, namely that it is a 15 kilowatt machine with a synchronous speed of around 150 RPM. Also shown on the slide is a simplified line diagram of the test bench layout, which shows the variac. An external three-phase inductance was added to the terminals of the generator, which effectively increases its synchronous reactance to around 0.64 per unit. This slide shows the measured results of grid current versus grid voltage and supply power for two test case scenarios, one where the added inductances were added and one where they weren't added. The red portion of the curves indicate where the supply power was kept constant at 0.2 per unit, and the dash blue indicate where the supply power was kept constant at 1 per unit, and the green indicates the analytical results. As can be seen, a good agreement between the measured and analytical results were obtained. The slide shows the reactive power versus grid voltage and supply power for the two test case scenarios where the added inductances were added and where they weren't added. Once again, it can be seen that a good agreement exists between the measured and the analytical results. What's interesting to note is that for figure B, where the external inductances was added to the generator terminals at low power conditions, that the slip synchronous permanent magnet generator acts as a passive reactive power compensating device, where it supplies reactive power where the grid voltage drops and it absorbs reactive power where the grid voltage increases. This is typically how grid voltage compensation is done. In conclusion, the optimum reactance matching between a permanent magnet synchronous generator and the grid is investigated. The best overall results are obtained for a synchronous reactance of 0.5 per unit and a back EMF voltage of around 1.05 per unit. It was also found that increasing the synchronous reactance between the generator and the grid has the effect of decreasing the generator's sensitivity towards grid voltage variations. This outcome allows engineers to design generators according to the required per unit synchronous reactance and back EMF voltage values that will yield the best results for a specific microgrid. Thank you.
So thank you for your presentation, Dillan. And please post your questions to the audience. Please post your questions on the question panel. We'd like to hear from you if you have any questions for Dillan. While we're waiting for the audience to post any of their questions, I have a question for Dillan. So Dillan, thank you for that presentation once again. Maybe you could just tell us, I have a couple of questions. The first one is, and this might not be the sum total of your research, but perhaps you can tell in terms of the fluctuations when it comes to the source. Have you considered that or looked into that?
By the source, do you mean the wind or?
Wind, yes.
Yes, so typically, normally direct grid connected synchronous generators aren't really the way that wind turbines are constructed. Typically, the generators, especially permanent magnet generators, are connected to the grid by means of a full rated converter. And the full rated converters, one of its responsibilities is to damp the fluctuations caused by the wind that oscillates through the drivetrain. But for the slip synchronous generator, the slip permanent magnetic coupling, if I can go back to this slide, it is responsible for damping the fluctuations caused by the wind. It operates similarly to a permanent magnet induction machine, where the slip portion of the slip permanent magnetic coupling, that slip function dampens those oscillations.
Okay. Okay, thank you. So we have a few questions. Perhaps we can just go through them. The first question is from Anthony. Could you please explain how the power factor was controlled and at what level it is the most optimum?
Okay, so the power factor, couldn't really be controlled because it is a normal permanent magnet synchronous generator without any field windings. So its power factor is completely dependent on what's happening with the grid. So all that we did was we just looked at what would happen to this particular machine's performance when we manually vary the grid voltage, or we manually vary the input power supplied to the generator. And for this particular machine, it was found that ideally its optimum power factors obviously would be 1, but it was designed to be able to operate at around 92% efficiency for a power factor of between 0.92 and 0.95, if that answers the question.
Yeah, thanks, Dillan. So just the next question, what will be the losses, the additional reactance between the generator and the grid in reference of the power generated by the generator? That's from Peter Fick.
If I understand that question, is it what would be the added losses caused by the externally added impedance?
Yes, that's it.
Yes, so yeah, that would be that would vary as the losses is a function of the wind speed, which varies considerably. But obviously, we'd want to minimize those losses, and those losses are purely a function of that external impedance. In our testing, we just used a 16 millihenry external inductance, and the resistive portion of that inductance was quite low. We couldn't accurately measure it, but obviously during the design optimization of the synchronous generator, which includes this externally added impedance, you'd optimize it to minimize those added losses. That answers the question.
Okay. Okay, so we're going to take a couple more questions. Fortune asks, synchronous condensers are either 4 or 6 pole machines, high-speed machines. I see you have used very slow speed 40 pole machine. So what could be the reasons for this?
So in this case, the machine was designed to operate at a small wind farm at Stellenbosch University, and it has a maximum power rating. Let me first start with our lab can only measure machines rated at around 15 kilowatt. I think it peaks at 20 kilowatt. And during the design optimization, we found that a 40 pole number machine would, at that synchronous speed, would provide the 50 hertz grid voltage. Obviously, we could increase the pole number to decrease the speed, and that is being looked into. But for this, because this slip synchronous design is still in its initial phases, we decided that this specific design would provide the results that we were looking for.
All right, so thanks Dillan for that, answering the questions. There's a couple of other questions that I think we're not going to be able to get to, but we will certainly put you in touch with Dillan, and perhaps you can, he can get back to you on the rest of your questions offline. So thanks once again, Dillan, for your presentation.
Thank you. Thank you.
So I'm just going to get to our next presenters and set of presentations now. So this will be on the rotating machine section courses, and some of the course developers are going to be presenting a synopsis of their courses. The first presenter is Henry. Mr. Dupree is an SAIEE Fellow and an independent consultant with over 58 years experience since first graduating at the University of Witwatersrand. Henry specializes in electrical machines, both AC and DC and transformers. He has extensive experience in the mining industry, including the repair and consulting fields. He offers a range of specialized training courses in association with various companies and SAIEE. Henry has consulted and traveled to a number of different countries, consulting, analyzing faults, and witnessing tests with regard to machines and transformers, including the China, USA, Oman, and many more. Henry, I'm going to hand over to you to give us your presentation.
Very much. Sorry, I'm just trying to get it onto a slideshow. Some reason it's stuck there, not on slideshow. Thank you very much, Wesley. Sorry? Okay, I was trying to get the slides to fill the whole screen. For some reason, it just doesn't want.
Yeah, Henry, I think you can just click on the current slide.
Sorry?
Bottom right, at bottom right.
Bottom right.
Yeah, there's that like a window house type of a thing.
I just can't get that. Sorry about that. Is it that one? No. I can change the screens, but I can't get slideshow to go straight. You say bottom right.
Yes, there's just a button there on the right at the bottom. Wesley, do you have a screen there that you can put up on your site already in the correct format quickly?
Maybe we can go on to Lissetti.
Yes.
In the meantime, suggestion.
Okay.
Yes,
okay.
let's please do that. Okay, sorry about that.
No problem, no problem. Lissetti, you ready?
Yep.
All right.
So I can just, let me just introduce you, Lissetti. So we're just waiting for Henry to get his presentation together, and then we'll hear from Lissetti in the meantime. So Dr. Lissetti, CC, received the BSc and MSc degree in 2007 and 2009, respectively, both in electrical engineering from the University of Witwatersrand. He was appointed as an application engineer at the CSIR in 2009, completed his PhD degree in electrical engineering at the University of Concordia in Montreal, Canada in 2015. He was then appointed a project manager at the CSIR in Pretoria. From May 2017, he joined the University of Witwatersrand as a senior lecturer in the School of Electrical and Information Engineering. He is the curriculum committee chair for the school, and is currently a lecturer, member of Senate, a senior member of the IEEE, He's a council member of the SAIEE and serves as the student chapters and centers liaison chair. So he is a guest editor of the SAIEE Africa Research Journal. He's a review of a number of high impact factor IEEE journals and has published in numerous technical papers. Dr. Masisi is a Y-rated researcher, and his publication topics include permanent magnet synchronous machines, variable flux insert, PMSM, synchronous reluctance machine drives, multi-level converter-based electric drives, and their modulation strategies. So I'm going to hand over to you, Lissetti, to give us your presentation. Thanks.
All right. Hi, everyone. Thank you for that, Wesley. All right. I'll just give a synopsis of the course module, the rotating machines, one of the course modules in our rotating machines we'll be offering. It's in field of electric drives and their applications. All right. The course overview is as follows. We will be looking into variable speed drives and their applications, particularly also to high performance machines. And historically, we are familiar with the classical control techniques, such as the V/F control, and then we'll delve into field-oriented control or vector control, and also direct torque control techniques. We will also look into the other converter topologies and their applications. And as you know, a drive, one of its hardware components is a converter or an inverter. So we'll be looking at three-level inverters, or what is normally called multi-level converters. What really are their advantages, and what's the motivation really behind going high-level converters topologies? And then as well, looking at applications in marine, there is an increase of the usage of more converters, and also looking at high energy efficient switching devices, the wide band gap devices such as gallium nitride and the silicon carbide devices, how they are really revolutionizing drives or variable speed drives. We'll also look into electrification of transportation. As you know, there are plans 2050 in many countries to electrify transportation, to reduce the use of internal combustion engine into using the use of electrical machines. So we'll be looking at the motivation, the history of transportation, electrification of transportation, and also various topologies actually of those drives. We'll also be looking at traction models, because I mean they form the heartbeat of the electrification of transportation. We'll be looking at different automotive companies, various machines, and what makes those various machines unique in those various companies. And also we have a case in point. A study was done on a variable flux machine. So we'll be looking at also at the benefits of a variable flux machine and what it is actually, this variable flux machine. And then electric vehicle powertrains. You have noticed that especially in the mining industry, these heavy haul mining vehicles, when they go uphill, they actually convert from the use of diesel to electric drive. So we'll also be looking at that, and how are they really benefiting in terms of the fuel consumption when they use an electric drive system. And also more electric aircrafts, the future, how it's looking. You might have also seen that this research in those areas to reduce the use of jet fuel into having more electric aircrafts. And really, how does the future look like, and some challenges. So just a synopsis. Usually on an electric motor drive, the hardware components are generally same or similar, whether it's a scalar type or a direct torque or a field-oriented control. So the main focus will be really on this controller there. When you have to use vector control or field-oriented control, what is that really, and what makes it advantageous as opposed to a scalar type control, and what necessitates its operation to drive a machine, induction or a PM or a synchronous machine. And then we'll also be looking at traction drives. What is the composition of a traction drive? What are the limitations of a traction drive? And we'll be looking at different topologies of these traction drives for electric vehicles. As I mentioned also, there are various topologies in multi-level converters. They go to various levels, 12 and 6 and so on. However, we will just be looking at one case of a 3-level multi-level converter for drive applications. And as I mentioned, what really necessitates this in our day and time. And also a variable flux machine. This was a motor that was prototyped, built, and just to give you a brief advantage of it is that it uses permanent magnets, but actually these magnets, you can magnetize them and demagnetize them on the fly. And this gives you certain added advantages actually, especially in traction applications, even for wind or energy applications actually. And then we'll delve into that. Why is that a benefit, or why would that be an issue? And then lastly, we'll be looking into high performance rotors. As I mentioned, different OEMs, suppliers. This is a rotor of a Toyota Preez. That's a rotor of a Chevy Volt. This is a Ford. And this is a spoke type IPM motor. We'll be looking at some of these topologies, high performance rotors, and what are the advantages and disadvantages among them. So I really want to invite you all to be part of this course, this session, where we can really go through some of these concepts together. Thank you very much.
Okay, thank you, Lissetti. Maybe we can go back to Henry now. So Henry, you can go ahead. Thanks. Henry, maybe
yes, I didn't. Okay, we're going to look at motor management. I think that's important from a operation point of view and a maintenance point of view on motors itself. We're going to look at various types of motors, some of the theory about motors, and the operation and repair of machines and some problems. The course will sort of cover an introduction into motors itself, some history about the motors, some basic theories, the types and characteristics of various motors, motor selection for a particular application, starting methods, good winding practice, including repair consideration. This, I believe, is important from a maintenance point of view, and people that have to have motors repaired by various companies that exist in South Africa, the testing of the motors, installation considerations, another important factor, the motor's installation itself. We've had a number of problems on installations where motors have failed prematurely because of poor installation, the maintenance on the machines, and then some interesting failures and faults on the machines itself. We'll look on the motor management wants to say on AC motors, induction wound rotors, synchronous permanent magnet motors, and linear motors. DC moters, the shunt series compound and permanent magnet DC machines, their application and the characteristics of these machines, which I believe is important on selecting the correct machine for the particular requirement. That's understanding the applications and the starting of the machine, which is the best way to start to get maximum torque or reduced torque on the machine, because there's certain applications where we don't need very high torques. As I mentioned, the characteristics of the machine, the maintenance, the repair and good winding practice, and faults on the machine. Back, we're going to look at, I think, some of the interesting where machines started, a little bit of the history of the machines, and then the modern machines, DC machines, AC machines, and some very large AC machines, which are particularly slow speed. Good winding practice, look at what can be done to maintain efficiency on rewinding a machine, improving efficiency, and keeping the life of the machine for expected values. I have a number of photographs and calculations on what we consider good winding practice. Some photographs on, again, on the machines and why it's important to have a certain amount of lashing on the machine and support on the coils to maintain and restrict the movement of the coils itself. Because any movement on there could cause chafing and damage to the coil and premature failure on the machine itself. Partial discharge comes into good winding practice as well. I know Rob in his session will be covering partial discharges, which is related to the spacing of the winding and the overhang in that. It's a slow process, but the partial discharges do eat away the insulation well. As you can see, that section there and the section here where we opened that and saw how the insulation had been eaten away, and we would expect premature failing at that particular spot on the winding. Testing of new and repaired machines. We'll discuss AC machines and DC machine testing. Should be noted that no load testing, locked rotor testing, and the winding insulation testing performances is generally sufficient to prove that the repaired machine or the new machine will meet the requirements required, except of course in some new designs where something is coming where you may want to do some full load tests on the machine. There are a number of companies in the country which do full load tests on AC machines. DC machines is more critical from a point of no load conditions do not indicate anything about the commutation on the machine, whether the intervals are correct, compensating windings are correct, and generally DC machines would require some load testing of some kind, a back-to-back type testing, which if you have two machines works very well. So that will be discussed in the papers itself. Installation. I have some examples of poor installation where machines have failed because installations were not adequate and direct online starting hadn't been taken into consideration when they designed the base plates and foundation of a particular machine. So installation is an important factor. And then I have some interesting slides of various failures on machines, rotor failures, other failures in the machine itself, and we can discuss why we believe the failures have occurred and what to do to prevent them in the future. Had die-cast aluminium rotor failures. We've had rotor failures on bar wound rotors, and we'll discuss those as well. I'd like to thank you and trust you'll find the training of interest and of benefit if you do decide to participate in the training. Thank you very much.
Great. Thank you, Henry, for your presentation. So we're going to move to next presenter, who is Rob Malaya. I'm just going to give you a short bio of Rob. So Rob graduated in electrical engineering from the University of Witwatersrand, and from Witwatersrand in 1993, where he developed a passion for electrical machines that remains with him until today. So this passion resulted in his first engineering position at ABB AC Machines in Elroad, South Africa. After almost 10 years at ABB, Rob moved to a small specialist condition monitoring company, Westwood Electric, but subsequently rejoined ABB a year later as Strategic Development Engineering Manager to feed his passion for rotating electrical machine failure analysis, diagnostics, design, maintenance management, and above all, problem solving. Rob joined LH Martinussen in 2006, where he remained until August 2013, leaving as Rotating Machines Technical Executive. Rob remained in Atom Group, however, moving from LH Martinussen to Martinussen and Coutts in September 2013, where he has remained responsible for engineering and technical management. Rob has presented courses and authored and co-authored articles both nationally and internationally. He's a member of the SAIEE, a past chairperson of its Rotating Machines Section and current chair of SAB's Rotating Machines Technical Liaison Committee, TC2, to the IEC. Robert has also chaired Electrical and Allied Industries Association and is a member of Wits University's and Northwest University's Industrial Advisory. So Rob, I'm going to hand over to you to give us your presentation. Thank you.
Thank you, Wesley. Can everybody hear me?
Yes, you can hear you, Rob.
My screen.
Loud and clear. Thanks.
Okay,
Yes,
thank you. You just taught me something new today, Lissetti, this laser pointer. I quite like it. Okay, my course is quite, it's sort of a, when I looked at it, I'd say practical aspects of rotating machines. If you look at the content, you'll actually see it's all about getting the most out of your industrial machines, i.e. preventing failures, what you can do to prevent failures. So there's some design aspects. Mostly it's condition monitoring, testing, and then I look at two specific types of specific failures that occur on machines. It's very practical, but you'll see that we go into some fairly advanced testing methods like partial discharge, rotor flux, and even vibration can get very advanced for an electrical engineer or a practitioner in general. But it's in a hands-on, easygoing manner. If you want to see the sort of presentation, you can go onto the SAIEE Rotating Machines Section website and have a look at the presentations. They're quite nice because they're in video form, so you get a very good idea of what it'll be like. You'll see all the topics that I mentioned will be covered, but it's a very wide field, and I like to look at what the membership or the delegates are on the day and concentrate on a few specific aspects. So it's quite flexible in that respect and maybe quite useful to some of you to look at specific problems. And then you also see that a lot of the topics covered are mechanical in nature, and that's specifically vibration. So let's look at we'll look at maintenance, diagnostics, and condition assessment. So how do we, in order to troubleshoot or prevent failure, we need to solve problems, and we need to know what causes these problems. So what causes the failures? So we look at team stresses. That team stands for thermal, electrical, ambient, and mechanical. We look at remaining life assessment or remaining life prediction, the difference between diagnostics and condition monitoring. Then the specific testing we look at, partial discharge analysis. We look at asset management basics, root cause failure analysis, and rectification. That's very important. It's one thing to identify the root cause of a failure and another thing to rectify it. And leading on from rectification is refurbishment and redesign. Those of you in the maintenance and repair industry will realize that sometimes the repair of a failed motor involves a redesign, even of more modern machines. Why insulation is so important for failure prevention? And then the second one on that is bearings, because they're the two most common failures. Vibration, we had a discussion amongst ourselves, and we'd like to propose that we do vibration, but not necessarily in detail in this course, but in a separate course. So those of you who are interested in vibration, it's available as a topic on its own that we can discuss. You can discuss with the rotating machine section. Then this is an example of one of the slides from what part of the course, and it's on shaft voltages and currents. Why are shaft voltages and currents important? Because they are one of the primary causes of bearing failures. And then there's also a section on bearing failures. A little bit more detail of what we do. Maintenance and operation, as I said, it's getting the most out of your machines. So preventing failures. You could go into things like total cost of ownership, but it's really practical. So it sticks to the real basics of getting the most out of your machine. So it's testing, monitoring and diagnostics, and then some design aspects, like for instance, the dielectric stress on insulation in a stator. It's a very interesting topic to delve into, and one that you can, as a purchaser of a machine, you can specify to the OEM. Then we look at specific testing. I already mentioned partial discharge. Look at tan delta, the difference between the two and where both are headed. Vibration, I've mentioned, and then rotor flux testing. This is a method of detecting interturn faults on synchronous machines. It's becoming more and more common, and it's extremely accurate on certain types of machines and very well worth knowing about and understanding. Then the last two things I mentioned specifically, electric motor bearings, preventing failures, getting the best out of your bearings, and linked to that, shaft voltages and currents. Understanding the causes, preventing damage, and then shaft brushes is quite a topical subject at the moment. Example of this is the list of the topics under preventing bearing failures. As I mentioned, a lot of electric motor failure mechanisms are mechanical, and I like to often say that electric motors are 80% mechanical. Thank you very much.
Okay, thank you, Rob, for that presentation. So I've asked in the chat for anyone who has any questions or comments or even ideas and feedback for Rob, Lissetti, or Henry regarding the courses and a kind of synopsis of the courses that are planned for the rotating machine section. So you can post your questions, and we'd like to give them some feedback regarding the courses as they develop them and offer them. So please post your questions or comments in the panel. Before we hand over to back to Jabulani to close the session.
Is it Werner? Werner, do you want to say something? I see Werner's got a question, Wesley.
Okay. Just have a look at the question there. Yep. So yeah. So there's a question to Lissetti from Karabo regarding. I would like to see the application of parameters on variable speed drives. So I guess Lissetti, if you want to maybe give some feedback or comment on that.
Can you repeat? I didn't get the question, Wesley.
It's a comment from Karabo saying that they would like to see application of parameters on variable speed drives.
Okay. So I think, yeah, the course would cover that.
Okay, great.
Okay.
Yeah. So this is a question, not too specific. So any of our presenters can jump into this. Rob, Henry, or Lissetti. So one of the questions was, what are the condition monitoring systems that are more efficient for rotating machinery from non-Wabisi?
Okay, I'll give you my opinion. I'm an electrical engineer, so I would like to say something non-mechanical. But in my opinion, the most effective, cost-effective, and useful and easy to understand method of condition monitoring on a motor is vibration. It applies to low voltage as well as high voltage machines. When it comes to insulation on low voltage machines, very difficult to monitor online, because the insulation is so thin that the failure can come very quickly. On high voltage machines, it's partial discharge. It's the only method of online monitoring on on insulation on a motor. The only commercially viable and available method. I hope that answers part of your question.
Okay, thanks, Rob. So the next question is, what are the best protection systems that can be applied on DC traction motors?
And if I see Henry is muted, I would.
Go on, Rob, carry on.
Brushes. Well, I would look at what causes them to fail mostly, and apart from mechanical, I would say mechanical failures, so therefore vibration. And then the second one is obviously the brush wear commutator. So something to look at that. It's quite an interesting question. I'm not a traction expert, and the problem with DC traction is that it's basically old and still in use, but it's not state of the art. So you won't find state of the art monitoring methods. I do know that what is often used in slip ring motors to detect arcing and sparking is arc fault monitoring sensors, and that might be an option. But that's as far as
Yes, so traction motors, of course, are very much more difficult because generally they're mounted in inaccessible places to check it. So, when you're looking at large DC motors on drag lines and shovels and all sorts of things like that, you can actually see the commutation and you can monitor it a lot easier. But traction motors being very compact and fitting generally on the axles underneath a loco and things like that, it's difficult. It's difficult to have those items done, and it's periodic checking and having a look at the unit itself. Commutation is the major problem that you have there, and obviously overspeeding and things like that does do some damages. So speed is one of the things that should be monitored on the locos. If they do run away or go fast, you tend to have problems. I have no other ways of detecting, brush wear on that other than physically going in and checking the commutation on the machine. Thank you.
Thanks, Henry and Rob. I think we can take one last question for Lissetti. Zolani asks, the course cover traction motors for rail vehicles, or will it only focus on traction motors for road vehicles?
It's mainly for road, but really the principle would be same between either rail or road. You know, the biggest difference that I see between the two is the size. You know, for rail applications, you have the luxury of the size. And what makes the on-road a little bit more complicated is because you really have a limited size. So your design really has to be very precise, and weight is your biggest issue because you have a limited energy source. Whereas for rail, you are more flexible in terms of size, dimension, volume, and you have the catenary system. So in terms of energy supply, you're more or less not really limited because you are basically linked to the grid. So, but I would say those are the two differences that I would just off my head foresee. But they are more or less the principle are same.
Thank you, Lissetti. It was. You want to, as the presenters had something to add? Anything else?
Could I just add on your DC mode and on commutation? There has been research work, and there are some units which basically look at the radio frequency inside of the motor. So a detector is fitted there, and if you pick up a lot of sparking on the commutation, it does tend to send the signal which you can monitor. I have never really used it, but I do know of it, and I know it has been fitted on some motors, but I've never seen it fitted on a traction motor, though. So it's in the DC traction motor application.
Thank you for that, Henry. So there are some other questions and comments. Thanks to the attendees for those. We don't have time to get to them, but we certainly taken note of them, and they will be passed on to the speakers as well, hopefully to get back to you. Now going to hand over to Jabulani to close.
Oh yeah. Can you hear me, Wesley?
Yes. Yeah. Thank you.
I think colleagues, you can all agree that we've had such a wonderful afternoon. The topics were on point, and I'm just in awe with the experience that is out there. I mean, I'm looking at Henry, I'm looking at Rob, and I've always been following Rob as like kind of a mentor in terms of the machinery. And I'm looking at Lissetti, a young guy, but he's so much experience. And then I think I must admit, I think we're all in good hands, and we're looking forward to the training that is going to be offered by this gentleman. I'm sure all of you are looking forward to it as well. And thanks to Dillan as well for his presentation, and we hope to see him more in the future to have the rotating machinery section as well in terms of new ideas, new ideas from academia as well. So I think, yeah, we can all agree that the training that is coming ahead is something to look forward to, and we're all looking forward to take part and make sure that we maximize our knowledge and also try to have more contact as well. Yeah, that's all from my side, and I don't know, Wesley, if you've got anything to say, and the presenters as well. But from my side, I think we've done very well, and we're looking forward to this training taking place.
Maybe Jabulani, just to mention to all the attendees that this recording of this webinar will be made available by the institute and on the SAIE TV. So thank you again for attending.
Thank you very much. Thanks, Wesley. Thanks, Rob. Thanks, Henry, Lissetti, and Dillan. Thank you very much. And to all our listeners, thank you. See you next time. Thank you very much. Bye.
Thank you, everybody.
Thank you. Cheerio.
Thank you.
Thank you.
Thank you, Joel.
Yeah, thanks, Joanne.
Yes.
Yeah.
Thanks very much, Joanne. All the help.
Yeah. So quite a good attendance, and hopefully we'll keep the same. We'll capture the same audience next time when we. So we'll make sure that we meet the expectations that we've definitely done so today. So thank you very much. Thanks to the presenters as well.